So what we're going to look at today is part of the Group 2 topic in A-level chemistry, so the alkaline earth metals. So we'll be visiting some of the things that we've looked at before in other topics, and we're predominantly looking at the trends in properties of Group 2 in this particular episode. Okay, so what I should have also highlighted here, so these are the topic overview. So today I'm going to go through the trend in atomic radius down the group, and first ionization energy down the group, and also the trend in melting points down the group. And I have got a slide in down here as well on the use of magnesium in extraction of titanium, which is a specific case example that we can look at. Okay, so moving straight into it. So look at what happens to the size of the atoms. So this is represented by the atomic radius as we go down the group. So here I've got a table of data, and I've included beryllium, although you don't always see that included. But we look at this data here, and we can see as we go down the group, the size of the atoms increase. Now, this shouldn't be a big surprise because things we've looked at before, but it's just a chance to refresh ourselves on our explanations. And our main explanation is that the size of the atoms essentially is decided by where the outer electron is. So here in magnesium, I've only got 3 energy levels completed, whereas I've gone down the group in barium, I've got 1, 2, 3, 4, 5, 6 energy levels with electrons in. So these outer electrons here, which is dictating the size of my atom, are a lot further away from the nucleus. So always remember just to build that idea of where the outer electrons are and the distance from the nucleus. Okay, so first ionization energy. So topic we've looked at before in a couple of guises. So here I've got some table of data, but as a quick revision, let's have a look at what first ionization energy is. Well, it's the energy required 1 mole of electrons from 1 mole of gaseous state atoms. So for example, from that magnesium, it's going to be in the gaseous state. I'm going to apply some energy to it, and I'm going to be making a 1+ ion, and also that's going to be in the gaseous state, and I'm releasing an electron as well. Now, don't worry for the fact that magnesium forms a 2+ ion when in its reactions. We'll look at that in a minute. But at the moment, we're just looking at the first ionization energy. Pause that for a sec. So we're just looking at the first ionization energy of magnesium in this case, and all the others as well. And we can see on our graph over here that our first ionization energy is decreasing as we go down the group. So again, we're linking this back in to our size of our atoms, and the electron that we're losing when we're doing our first ionization energy is going to be coming from the outer shell. So for each of these is coming from the outer shell in the atoms. Okay, and those then are further from the nucleus, so they're feeling that electrostatic attraction less. And there's all that shielding of those inner electrons. So for example, down here, all these inner electrons here are going to be preventing the nucleus from attracting the outer electrons as strongly. Okay. Okay, so kind of explained on the previous slide what the answer is here. So the outer electron is going to be further from the nucleus. The 1 electron that we're removing for the first ionization is subject to more shielding the further down the group you go. So barium, the outer electrons, feeling the pull of that nucleus so much less, so it's easier to remove. Now, I said before, we've got our first ionization energy. So I'm going from M to M+, so M just represents a metal. Remember, it should be in the gaseous state, and forming an electron as well. That's a negative sign there. Okay, so that represents the first ionization energy. So the second ionization energy is this data that we've got up there, and that's going from the 1+ ion. I'm just showing magnesium now randomly. again in the gaseous state. And then from this one, I'm going to form a 2+ ion. So this is the second ionization energy. Apologies for my writing, for my stylus is still rubbish. So this transfer here is represented by the numbers in this column. Okay. When we're forming an ion, it's going to be the sum of the first ionization energy plus the second. So plus that. And that is the energy required to form our 2+ ions, okay, from the atoms themselves. Okay, that's all I've just shown on here, just to for us to see that our sum of our first and second ionization energies is also decreasing down the group. So we know we form our 2+ ions, and it's easier to form the 2+ ions as we go down the group. So our reactivity down the group is going to increase. Okay, so reactivity increases down the group. Okay. Right, flipping over. So the trend in melting point. So we need to kind of look at this. Well, we do need to look at it. And it is a slightly messy story. The reasons for it we don't really need to know, but magnesium doesn't fit the trend. So these three, calcium, strontium, barium, nice trend we can see up here on the graph. Melting points decreasing down the group, but magnesium is an exception to the rule. Okay, the reasons we don't need to know. But, for example, I'm just going to do a little representation. One of the arguments is that it forms a different crystal structure. So the way those atoms are packed together in the metal lattice are different. So, for example, you could have a metal lattice where our atoms are arranged in kind of rows like that. Or you could have them where the atoms are arranged slightly differently. Like this, and this would give different properties. Okay, and some of the properties this may affect is the melting point, as the atoms are more closely packed together. But like I said, we don't really need to know that. So I'm going to erase all that stuff on there. Okay. So what do we need to know on these? Well, it's kind of the similar arguments that we've looked at in the past. So it's the size of the atoms that are going to make the difference. So up near the top of the group, our atoms are smaller. And if we think that within our lattice, we've also got our electrons floating around here. And we'd have an array of these things. And because at the top of the group, so for calcium, for example, because magnesium is the outlier, the ion centres of our metal lattice are that little bit smaller. So the charge density is greater for these. This 2+ charge is over a smaller volume, size, whatever you want to think of it, than it would be further down the group. So over here, a large one might be strontium or barium or something like that. That 2+ ion is sort of diluted over a bigger surface area. So the attraction to any particular point to these electrons is going to be less. So there's less electrostatic attraction between the electrons and a larger ion than it would be to a similarly equally charged smaller ion. Okay, so just reading what I've written down here. So smaller ions in the metal lattice have a higher charge density, therefore a greater electrostatic attraction between the delocalized electrons and the metal ions. So it's all about this charge density. Okay, so this is just a little bit of bonus material. This is about extraction of titanium. So titanium is a really versatile metal. It's used in lots of things, hip replacements and dental implants and all kinds of stuff. It's quite a high-tech metal, really. It's lightweight and very strong. It's quite an abundant metal, and it comes from this stuff called rutile. So that's titanium oxide. I'll change my pen colour because that's a bit rubbish. Go for something over here. So this rutile is titanium oxide. We could extract it by carbon, but what happens is, as well as forming some carbon monoxide in it, we form this stuff called titanium carbide. And this messes up any metal that you do make. It makes it quite brittle. So what they do is they take our titanium oxide and they react it with chlorine in the presence of some carbon, and they make this stuff called titanium chloride. Okay, sometimes it's called tickle. So it's this titanium chloride which we then reduce using magnesium. So our magnesium, we need a couple of these. So this magnesium, in the old days, you'd probably call this a displacement reaction. You know, think about GCSEs, we would be displacing the titanium from this titanium chloride compound to form magnesium chloride and our titanium metal. Now this titanium metal that we form here is not necessarily great, but they then go on, they can purify it afterwards. So, so this is the main idea here. It's just the use of magnesium with this group 2 metal to displace titanium from titanium chloride. A lot of the details you don't need to really know about this, just be able to explain what's gone on there. Okay, so last page. So what we've done today is we describe the trend in the first ionization energy and how it decreases down the group. And we've talked about how it's this electron being further from the nucleus and less attracted and therefore more easily removed. It also looks at relating that to the reactivity of them, so the first and the second ionization energies, and how towards the bottom of the group that is also lower and therefore will be more reactive. We've described and explained the trend in decreasing melting points in terms of the charge density on the metal ions in the metallic lattice. So this is where the further down the group, the charge density decreases, therefore the attraction, the metallic bonding is less, and therefore the melting point will be lower. And then for the AQA guys, we had a quick look at the use of magnesium in a specific example of extracting titanium. Hope this was of use. Any questions, and just let me know. Okay, thank you. Goodbye.